Hey friends, welcome back. My name is Mark French and I'm the Aero Dude. Today I'd like to talk to you about a simple fluid mechanics problem that has a little more depth than you might guess. All we're going to do is figure out what happens when you drop a ping pong ball. Now in physics class, probably in high school, when you drop things you assume that the acceleration was just that of gravity, 9.81 meters per second squared. So if I drop something dense, like I've got a collet off of one of my CNCs, if I drop this, the weight is so large compared to any aerodynamic forces, it really does drop at 9.81 meters per second squared. Yep. What about this? This is light, and it doesn't have to be going very fast before the aerodynamic forces really start to matter, and we do have to account for those to get the right answer. So how are we going to do that? Do an experiment. Well, that's hard to do, especially in my little office. Let's write some equations. So let's start. I'll put the ping pong ball down here, hopefully someplace it won't fall. There it goes. I'm going to draw just the ball here. And there's its weight, and that's just mg. Right? Now in any problem like this, we're going to need a coordinate system, right? So let's assume that that's the origin, and that's x positive. Now remember, a coordinate system is just there for us. Physics doesn't know or care anything about your coordinate system. Physics just works. The coordinate system is for us, it's for bookkeeping. You can use any coordinate system you want, and physics doesn't care. Physics doesn't know anything about it. So as long as you execute the problem correctly, pick whatever coordinate system you want. It'll work. Now, it helps if you use a coordinate system that makes the problem simple. So this is a pretty simple one. So there's the weight down. Well, we already said that the aerodynamic drag could be large enough to matter. So let's add that. I'll just call that capital D here. Here's aerodynamic drag. So if you've had more than about one class in fluid mechanics, you'll know that the drag is this. It's CD 1/2 rho V squared S. There you go. So this is the expression for aerodynamic drag, and it's a function of velocity squared. This term can just kill you. This is going to get big fast. So let's make sure we know what everything is here. Drag is going to be a force, it's going to be in newtons. We're going to do all this in metrics. CD is a non-dimensional coefficient called a drag coefficient, and it just is a measure of how hard it is to push something through the air. So something really streamlined like a dart or a missile or something is going to have a low drag coefficient. Something like a ball is going to have a high drag coefficient. We're going to use 0.45. Now, if you look around on the internet, you're going to find out that there's a lot of different numbers floating around for this. 0.45 is pretty close for what we need. 1/2 is just a number. Rho is the density of air. Well, the density of air at sea level at standard temperature and pressure is 1.225 kilograms per cubic meter. Well, that's not where I am. I'm inside this building. We're going to assume that's 1.2, 6 over 5. That gets you pretty close. Okay, velocity we know, and S is the cross-sectional area of the ball. Now the ball is 40 millimeters. Let me grab this ball again here real quick. Ping pong balls are extremely standardized, and they come in two sizes. This one happens to be 40 millimeters, and its mass is about 2.5 grams, okay? Wouldn't do if every time you went to play ping pong, especially in like a tournament or something, the ball was always different. So they're very, very tightly controlled. All right, so let's see. Before we do any number crunching, let's think about this a second and decide what we think is going to happen. Our intuition isn't always good in aerospace problems, and this one it probably is. So let's try to draw a plot here. Let's say that that's time, and up here is velocity. Well, what will we expect? When I first drop the ball, just the instant I release it, there is no velocity. Velocity is 0, so there's no aerodynamic drag. At that point, acceleration really is 9.81 meters per second squared. And it'll stay pretty close to that until speed starts to build up. So we really do expect something that, pretty constant rate of acceleration. And that's constant slope because remember velocity or acceleration is the derivative of velocity. A is dv dt. As the velocity the ball builds up, we expect that force to get bigger, proportional velocity squared. Well, eventually we're going to get to the point where it's going fast enough that it stopped accelerating. That is, this number equals that one. They're equal and opposite. Well, you add up all the forces. If the forces add to 0 and F still equals ma, A has to be 0. So we would expect something here, and I'm going to call it VTRM, T-E-R-M, terminal velocity. This is what terminal velocity means. It means that the aerodynamic drag equals your weight, and so you're falling at a constant speed. Now, over the summer, I guess it was last summer, I went skydiving. I went tandem. There's a guy named Ali strapped to my back. Ali was great. It would have been really bad without Ali. And we bailed out of this plane at 13,000 feet, so that's like 4,000 meters pretty much, and started falling, and we reached terminal velocity pretty quick. Now, it was fast because Ali and I weighed a lot, and adding him to my back didn't change our cross-sectional area any, so we were going down at a pretty good clip. But fairly quickly, we stopped accelerating. We were at terminal velocity. So that's what that looks like. Well, let's start there. What would terminal velocity look like? Well, if this has to equal that, let's just write this down. Okay, the weight has to equal the drag. There. All right, so let's solve for terminal velocity. Well, how would I do this? Let's push everything but v over to one side of the equation. Let's write it out this way. All right, make sure I do this right. Looks like it's going to be 2g. Make sure I got that right. 2mg cd rho. Okay, that looks right. Square root. That's the expression for terminal velocity. Now we'll calculate this here in a minute. We're going to go on my computer and figure it out. So there's that. Well, that gets us this number right here. But we don't know what that curve looks like. Well, that seems like something we ought to be able to calculate, shouldn't we? So let's do that. Give me a second here. I'm going to erase stuff on my board here, and we'll clear out some real estate. Okay, in fact, I'll get rid of that too. Now, we all know the expression F equals ma, right there. Well, that's not actually what Isaac Newton wrote. He wrote something a little closer to this. Now, this is kind of using modern notation. In fact, that notation might be from Gottlieb Leibniz. Newton and Leibniz were kind of they lived at the same time, and they were basically competitors, I guess. So let's take that. Well, and it actually isn't force, it's the sum of the forces. If there's more than one force, you got to include them all. So we already know that mg is positive minus, okay, this is our aerodynamic drag force again. CD 1/2 rho v squared equals. There. Cool. Well, okay, we got a problem here. There's a derivative in here. Okay, it's just a slope. Well, this is a differential equation. Here's the thing. We're all conditioned to be terrified of differential equations. In fact, if you want to impress somebody and you're kind of nerdy, you go, well, I'm doing work in differential equations, and they're supposed to go, ooh. Well, there's no need. We don't need to do this. It's just an equation with a slope in it, and there's lots of ways to handle it. The easiest way to handle it is something called a finite difference approximation. And what that does is takes the differential equation and turns it into algebra with one assumption here, one approximation. We're going to be back in like 8th or 9th grade here in a minute. This is going to be great. So let's look right here. dv dt. Now these are just variables. That dv is a variable, dt is a variable. They're just variables. You can push them around like you do other variables. Now, they've got some very specific properties that you can't ignore. But at root, they're just variables. Well, okay, hang on a second here. I don't want to deal with a differential equation. The solution methods are very well cataloged. You probably take a class in it. But for right now, let's find another way. What I'm going to do here is I'm going to say that this is close to, in fact, let's do one other thing here. Let's divide through by m. Just to, we're going to need to, there. I want just dv dt. In fact, let's erase this too. There, clean it up just a little bit. Now, how big are those? Well, they're infinitesimal. What does that mean? Well, they're very, very tiny, but not zero. Let's do this. Let's replace that with capital delta V over delta T. All right? Now, what that means is, this is mathematician talk for, this is not infinitesimal anymore. These are numbers, and we're going to know what they are. Right? And the reason it's approximate is this is infinitesimally small. This is finite. And that's where you get the idea of a finite difference. If I make delta T small enough, I'm still going to get pretty much the right answer. You know, the difference between my approximate answer and the exact answer is going to be negligible. All right, negligible is something I can live with. So how do you do this? Well, what I'm going to do is I'm going to take my time and I'm going to divide it into concrete finite steps, delta T, and I'm going to calculate slopes. Well, what would this look like? Well, let's see. I think I call it I on the computer, so I'm going to use subscript I. That's still bad, isn't it? I can do better than that. There we go. All right. That's the definition of a slope. Well, that's a slope. That's the definition of a slope. Should work. Now, again, these are finite. We're going to know what these are. And when I do this, actually, let me erase some more stuff here. There. This is going to equal that. Now, these subscripts are going to refer to my steps, or be a function of my steps in time. That means this down here also has to be I. Now, I'm using something called a forward difference. There are others, but this is pretty well suited for what we want. So what's going to happen here is if I know a value of V, I can calculate the next one. If I know that one, I'll calculate the next one. When I know that, I'll calculate the next one. And we'll just step forward in time. Now, for this to work, I need to know one velocity. That's called an initial condition in this case. Well, go back to my ball here. When I drop this thing right there, the instant I let go, I've let go of it and it's hardly moved, what's its velocity? Well, 0. Okay? It doesn't stay there, but it starts there. So let's see. V0 equals 0. That's what's called my initial condition. Once I know that, then I can go V1. I'm going to find out what that is, and then if I know V1, I'll find V2, and around and around and around we go. So all I got to do now is I want to write this so that I've got V of I plus 1 on one side of the equal sign and everything else on the other. So give me a second here. I'm going to clean this up on my board, okay? Okay. Okay, let's check and make sure I got that right. G, C, D, there's the 2, rho, VI squared S, okay, and there's the M, that looks good. Multiplied through by delta, okay, that looks good. All right, what I've got now is an expression. If I know, let's say I equals 0. I know V of I equals 0 there, and I know it's equal to 0 there. V1 is going to be G delta T. Well, that's what you got in physics class in high school when aerodynamic drag didn't matter. Well, now I know what V1 is, and it's not 0 anymore. I'll plug it into there and calculate V2. And around and around and around we go as long as we need to. So let's stop with the board here, and let's go to my computer. I'll work it first in MathCAD, and then I'll work it in MATLAB for you.
Okay, here we are in my favorite number crunching program. This is MathCAD Prime version 10.0. Now, MathCAD is not a great name. It doesn't have anything to do with CAD. But this is a very simple program to use. It's the easiest way I know of to beat numbers out of a computer. And it looks like a scratch pad. So what you see on the screen looks kind of like what you'd write down. And it's live, so it recalculates kind of like a spreadsheet does. It's really handy. So let's run the problem in MathCAD Prime and then move over to MATLAB, which is kind of the standard number crunching program. And we'll see what the same solution looks like there. So if you look at the screen here, I've got all my parameters assigned right there. Here's rho, 6 over 5 kilograms per cubic meter. Now, remember that MathCAD Prime does track units. And the nice part is, you just type in whatever units you happen to have, and it converts everything into metric internally. So I happen to know this ping pong ball is 40 millimeters in diameter. If I knew its diameter in inches, I could just type it in inches. You know, what if it was, I don't know, 1.3 inches in diameter? There. It recalculated everything. Now, I'm getting a different answer because I kind of made that 1.3 up. But the point is, it didn't mind that that was inches. So I'm going to go back and fix it. I'm going to unbreak it here. There we go. So we get to recalculate. There we go. So now we're back to the right answer. The mass I typed in grams. That's just what I happen to have, and it converted it to kilograms. CD is unitless. G is 9.81 meters per second squared. And I had it calculate the area. Now I happen to know diameter rather than radius, so I just said pi over 4d squared. That's the same as pi r squared. And there's our expression for terminal velocity. And you can see right there, let's see if we can do, there we go. I got 8.5 meters per second. That's not very fast. You know, that's a very human-sized magnitude of velocity. And here's my finite difference solution down here. I guessed that I wanted to calculate for 3 seconds, so I said t final is 3 seconds. I wanted 100 points. I wanted to count from 0 to n. Now, if I'm going from 0 to 100, remember there's actually 101 points because we're starting at 0. And so there's my t, delta t. If I want, I can get myself more decimal points there. Give it, no, it doesn't need any more, so it won't write out anymore. So I calculated all my values of t because I'm going to know those beforehand. And then there's my initial speed right there, initial velocity. In math terms, it's called an initial condition. And there's, right there, that's the equation I wrote on the board. And so if I know v of I, I'm going to calculate v of I plus 1, where I goes from 0 to 100. So I did that. Now right here, I got to explain what this is. There's a little bit of bookkeeping going on. I defined 101 times, with the first one being 0. But because of that I plus 1, it actually has 102 values of velocity. And if I want to plot one versus the other, I think it's going to croak if I do it because the length of the velocity vector doesn't match the length of the time vector. So I just added one more time to the end of it manually. And so when I go down here, all I did was plot time and velocity, and there it is. Now, if this is correct, this should level out at about 8.5, and it does, 8.5019. So it looks like I've got the right answer. You can see that the acceleration is pretty constant at low speed, but as the velocity goes up, velocity is on the vertical axis here, velocity goes up, the drag goes up, and eventually the weight and the drag equal one another. If there's one thing I don't like about this right now, it's got really terrible step sizes on the vertical axis. So if I just define the first one, it should recalculate for me. There we go. All right. And same thing here. I'm not a huge fan of this. Let's make that 2.5 and see what happens. There we go. That's a little better. All right. Since that's correct, let's stop here and move on to MATLAB. Okay, here we are in MATLAB, and I wrote a little function called ball drop that does the calculations we saw before. You can see the first few lines here set up all the parameters we need. The duration of the simulation is t sub f, and there's our time step. So I calculated the terminal velocity right there, set the initial condition, and I made a little loop here to calculate all the velocities we need. Right there you can see I've added that final time step we need so that the number of t values and the number of v values is the same. And as a reminder, that I plus 1 means we're going to get n plus 1 values of v, so we've got to have n plus 1 values of t. I have to do it down here, because if I do it up here, then we'd have n plus 2, because it goes on. And so calculate the final time step and then plot them. So let's see what happens here. Let's take a very small number of points. Let's just say 10. Well, there it is. That looks pretty good. Let's blow this up a little bit for us. And you can see it's pretty blocky. You can see that the time steps are pretty big. Let's go here and see what that last data tip is right there. It's 8.502 pretty much, so I'm right on the money there. Let's try something else. What if I try to make this smoother? Ooh, it looks smoother, doesn't it? And the data tip, ooh, look at that. Now it's 8.488, so it's actually a little farther from my terminal velocity. What does that mean? Well, notice the slope here isn't exactly zero. As I get a more accurate simulation, what I'm finding out is that it takes more than 3 seconds to reach terminal velocity. So maybe let's move that up to 5, and let's hit that. Now let's go. Now we're up to 5 seconds on the simulation. And let's hit that data tip right now. Oh, look at that. 8.50185, and terminal velocity is 8.5019. So I'm pretty much there. So there you go. This worked. So we set everything up, set all our parameters up, calculated terminal velocity, and used a finite difference approximation to show how velocity increases with time, and the final velocity matched terminal velocity. So there we go. I hope this helps, and we'll talk to you next time.